All right. For those of you listening at home, hi Jana. We're praying for you. Gentlemen, best friends, conversations, pull the plug. I need your attention today. It's going to go fast and furious. I want to give you some time to work as well. Take out to our worksheet, please. I believe it was 7E. The next verse. Let's see. Yes, and I saw that again. If it ever does, you notice there's something else in the Alright. So 7E. Grab a red writing utensil. Here we go. Number 1. There are two strings of solutions for number 1. There's 120 degrees plus 360 degrees K, K is an integer, and 60 degrees plus 360 degrees K, where K is an integer. Number 2, there's only one string, 330, well actually, no, there's two, sorry, my fault. There's 30 plus 30 plus 360 degrees K, and sorry. Oh no, I'll go in and fix this thing, sorry. There are two of them, 150 plus 360K, and 330 plus 360K. Degrees.
What one was that?
Number 2. So it should be 130, 150, and 330, plus the 360K, blah, blah, blah. Yeah.
Well, I guess it doesn't matter, but do you always want us to put like K belongs to CN?
Yes,
At the end?
because if it doesn't, then people assume that K can be any only way one, including decimals, which would mess up your answer. Yeah.
For number 2, isn't like negative radical 3, wouldn't it be 120 and 300?
It is not. Part of the, eventually, if you do that right hand side, it's negative 5 plus negative radical 3 over 3. Negative radical, the negative 5's cancel. Negative radical 3 over 3 is downward slope a little bit.
Yeah.
Everyone. Number 3, there is one string, 90 degrees plus 360 degrees K is an integer. Number 4, two strings. It's actually pretty much identical to number 2. It is identical to number 2. So 150 degrees plus 360K and 330 degrees plus 360 degrees K. K is an integer. Number 5, no solution. Number 6, two strings, 60 degrees plus 360K and 240 plus 360K. Number 7 is no solution. Number 8. Oh, this is interesting. 7 through 12, it just says solve for regular from 0 to 360. Did everybody else do the 360K? Yeah, I wanted it too. I don't know what the worksheet computer did. Anyway, number 8 is supposed to be 120 plus 360K, blah, blah, blah. The other one is 240 plus 360K, blah, blah, blah. Number 9 is absolutely identical answers to number 8. 120 and 240 are the root solutions. Number 10, two strings, 90 plus 360K degrees, and 270 plus 360K degrees. Where K is an integer.
90 and what?
90 and 270, that's the two base ones. Number 11, there are two base answers, 0 plus 360K, and 180 plus 360k. By the way, the 0 plus 360k, I suppose you could just do 360k if you wanted to. And number 12, there are two base roots, 45 plus 360 degrees k, and 315 plus 360 degrees k, where k is an integer. Interview these. Questions? And if you want to see dissected. How'd it go? Easy, hard, medium? Did we do this on test? Doing okay? Any of them want to see? Yeah.
You use 12.
12, yeah. Scroll down. Okay, 3 minus cosine of theta. Equals 6 minus radical 2 over 2. What I would do on the right hand side, oops, sorry, divide this out, split it up. So 6 over 2 minus radical 2 over 2. So what this really is 3 minus cosine of theta is equal to 3 minus radical 2 over 2. I'm going to subtract 3 on both sides, because I'm trying to get cosine by itself. Negative cosine of theta equals negative radical 2 over 2. Divide both sides by negative 1. Cosine of theta is radical 2 over 2. And that's common. Yeah.
Can we do two?
Number 2?
Yeah.
We're not missing none of this.
Yeah.
And then cosine is what, Michael, on the unit circle?
Left, right.
Left, right. Does this look like a multiple of 30, 45, or negative? 45. What's that in radians? Just out of curiosity. Teaser for today. What's 45 degrees in radians? In the next week or so, your chore is going to be memorize some of the most common ones in radians. Like I've memorized 30, 45, 60, and 90. And then you can always find out the real ones. But, well, give it to me in degrees. Where are these? Cosine is positive radical 2 over 2.
So it's a little bit, or it's a lot.
Actually, there's only one choice. So it's 45.
Okay, so 45.
Yep. And where else?
There's 225.
225 is here.
Yeah.
Although that would make a cosine that's negative.
So, 135.
That's a cosine that's negative. Cosine is left, right.
So, 270 plus 45.
270 plus 45? Go ahead and do it on paper if you need it. Having a pen would be good.
315.
315. Okay. These are your two base angles. So what you do, theta equals 45 degrees plus 360 degrees k, where k is an integer. And theta equals 315. And then identical. Make sense? You can refer it down. And number 2, negative 5, it's a lot like this. On the right hand side, divide that out to negative 5 plus negative radical 3 over 3. So no, you asked about that one?
Yeah.
Okay. Do that first. Divide that, split it up. Negative 5 plus negative radical 3 over 3. Then add negative 5 both, add 5 both sides. You'll get tangent equals negative radical 3 over 3.
Yeah.
And then that'll be downhill a little. So you get 150 and 330.
Why not, radical three is down a lot?
Radical 3 by itself is down a lot. Radical 3 over 3.
How do we get over three again?
Ah.
When I worked it, it's got
Negative 15 minus radical 3 over 5.
over three.
Over 3, sorry. You got to divide both of these. Dividing the whole thing by 3 is the same thing as dividing each one by 3.
Well, isn't negative five on the other side too? Because if you multiply both sides by three, you get negative 15. And if you add negative
What was the other side? I forget. It was negative 5.
negative pi plus tangent theta.
Tangent of theta. And then equals, simplify this.
Negative pi.
And then this doesn't simplify.
Yeah, right, you're right.
I would add 5 to both sides. And then tangent of theta equals this. So you'll have a 3 on the bottom. And then you'll get a minus.
I multiply both sides by 3, try to cancel it that way.
Well, I want the tangent by itself. That would make 3 tangent of theta, which is too big. Okay. Any others? Good, okay with that? All right. Today, take out your notes, please. Is the first, and maybe for another 15 minutes or so, is a crash course in how to use radians. There are 2 ways to use radians. One is to take degrees and convert. The other is to think in radians in the first place. Draw, if you will, please, 2 unit circles, side by side. Ladies, I need your attention. I would like you to mark all the common angles on both circles. Do remember that the space in between 0 and 30 is twice as big as the space between the next 2 notches. So do not put the, do not evenly space these 3, otherwise it'll be wrong. The first one's going to be in degrees. The second one's going to be in radians. While you're setting that up, can somebody tell me the definition of a common angle? How do you know if an angle is common or not? We've been doing this for like the last 2 weeks. How do you recognize a common angle or not?
Multiple of 30 or multiple of 45.
Right. Any multiple of 30 or 45, or 90 technically, I love 30 and 45 for it. So any multiple of 30 or 45 degrees is called a common angle. So if I start here, this is 0 degrees. What's the first common angle? So okay, count all the way around and give me all the common angles in degrees. Okay, 60, 90. This is too big. What's it? You gotta be 30 degrees over there. 120, keep going. Yep. 150, keep going. 180, keep going. Yep. A little too far. 225, keep going. 240, okay. 270. 300. Good. 330. That'll be good enough. And then zeros go terminal 360. What I wanted to show you, the multiples of 30. I mean, I don't really count the 180 and the 270 ones. But does everybody say those are multiples of 30? Including the big ones, the 90, 180, 200, 300. Can somebody tell me what 30 degrees is in radians? What is the one proportion that everybody should memorize? Yeah. 180. 180 degrees is how many radians? Pi. Can somebody tell me what 30 degrees is? What do you do to this side to get it down that far? Divide by what? Seconds. You have to do the same thing too. What do you get? Exactly. 5 or 6 is 30 degrees. That'll work for any angle, by the way. If you start with 180 equals pi, You can divide it down however far you want. So I want to show you the benefits of thinking in terms of radians. It's kind of like in the metric system. Converting feet to meters is an absolute pain in the neck. There is no easy way to do that. I think 1 inch is 2.54 centimeters, and it gets worse from there. But if you start thinking in meters, it's actually pretty easy. If you're going to say, well, how tall is it? You grab a meter stick. 1.74 meters. Easy. So 174 centimeters. Think in terms of radians. This is pi over 6. Everybody see what I'm doing? Does everybody agree that 60 is 2 30s? 30 times 2? Do that here. In other words, I'm counting by 30s. 30, 60, 91, 21, 50, 180. Can somebody count by this? I'll give you a hand. This is 1 5 or 6. 2 5 or 6. Keep going. Just count. 2 5 or 6. Now make sure you hit the multiples of 30. 4 5 or 6. Keep going. Yep. Some of these will reduce. Correct. I'm skipping that. It's not very hard. 9 5 or 6. I'm going to ask you which ones reduce in a minute.
Okay, great. 10 pi over 6. 11 pi over 6.
And then,
12 pi over 6.
yeah, 0 and then 12 5 or 6. Does 2 5 or 6 reduce?
Yeah.
What is it? 5 or 3. But that's how you get them in the first place. If I know it's a multiple of 30, I know it's a multiple of 5 or 6. Try this. What's the sine of 5 pi over 6? No, I'm going to set anybody. First of all, can you see what multiple it is? It's a multiple of what? Do this again. 5 pi over 6, it's a multiple of what thing we've seen before? Up here. Well, actually, I'll do the first one and you do the next one. It's a multiple of 5 or 6. How many 5 over 6s are there? 5 of them. Now, what you could do is go to degrees, because pi over 6 is really 30, and then multiply by 5 when you go over here. Make sense? Then you could figure out, oh, sine is up a little, blah, blah, blah. Let me show you an easier one. This is 1 pi over 6, right? 1, 2, 3, 4, 5. Done. Give me the sine value there. Anybody? It's 1/2. Done. Let me try another one. Cosine of 11 pi over 6. Now I'll draw, you don't have to, but I'm gonna draw a fresh in the circle. I'm just gonna mark the multiples of 5 or 6. Which I remember is 30 degrees. Let me show you. It's a lot easier than you think. Somebody tell me where this is in radians. Feet.
Would be 5 over 6.
5 or 6, what's this?
5 3.
True, but give me the unsimplified.
Oh, 2 pi over 6. 3 pi over 6.
Now do this. How many pi over 6s do we need? If I'm looking at this problem. Here there were 5 of them. How many here?
What's the number right before pi?
11.
Oh, would you need 11?
11 of them. Watch this. By the way, pi over 6, do you remember that the top half of the circle is pi? You just have 6 pieces. We'll get there. Does that make sense? So pi over 6 is 1/6 of the top. So 1 pi over 6, 2 pi over 6, 3, 4, 5, 6, 7, 8, 9, 10, 11. There we are. Can somebody give me the cosine? High five.
Radical 3 over 2.
Done. If you can think in terms of radians in the first place, these get a lot easier. You don't have to mess with converting back and forth, which is what takes all the time. Okay, let's try, this is going to be a little more intense. Tangent of 23 pi over 6. Go.
I have a question.
Yeah.
Oh, okay, 23, 5, or 6.
Now, does everybody see the pi over 6 buried in there? That's one of these things. How many of them do I need? Here I needed 5 of them. I need 23 of them. Here's what I do. Here's 1 pi over 6, 2 pi over 6, and then I don't keep saying it. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So you know once around the circle is 12. Now, can you just keep counting individually? Yeah, I suppose. What I do is I start saying 12, 24, oops, I went too far, 23. What's the tangent there?
It would be,
Positive or negative?
it would be radical, wait, it's negative.
It's negative.
Negative radical 3 and 3.
Got it. Done. Let me give you one even more intense. Yeah, question.
Wait, for the 45 angle though?
Oh, we haven't done those yet. We'll do those in a second. I'm going to make this absolutely ridiculous. Oh, 197 pi over 6. Now, if you like counting things one by one, you can. Does anybody have an idea what this is going to be like if you do that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now I just go, I got to keep going to 197. Does everybody say this is going to take forever? Here's what I do. 12, 24, 36. By the way, 10 times 120. See the trick I just did? 120 is a heck of a lot closer. And by the way, can anybody give me a multiple of 12 that's nice? 120 is nice, obviously. A nice round, yeah. 144. Okay, how many times would that be? 12 times around. 144. That's even closer. Can somebody give me something that's closer yet? So, does everybody see why I'm doing 12? Because there are 12 of these little clicks around the circle. 120 would be really nice. 144 is better. 192, how many is that? 12 times something is 192. That's beautiful, by the way. That's 16 times around the circle. How many more do I need? 5. Does everybody see that if you go like multiples of 12, you're going to end up at the beginning again? So 16 times, you're back at the beginning. I need 5 more. Click, 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 click. Give me the sign. It's 1 here. See how this works? Those are from multiples of 30. Now let's try multiples of 45. Can somebody refresh my memory what 45 degrees is in radians? Say again. How do you go from 180 to 45? Does it go unevenly? Yeah. It goes in 4 times. Divide by 4. Cut it in half, it's 90. Cut it in half again, it's 45. It's harder to see because it's a 5, and it doesn't go in quite as nicely. But you have to do it too. What is it? Okay. Pi over 4 is 45. There are 3 basic ones other than 180 equals pi, which is the basic one. I'd like you to memorize 30 degrees is pi over 6. 45 degrees is pi over 4. And if you can, memorize 90 degrees is pi over 2. Because those are the 3 multiples we're using. multiples of 30, 45, and 90. So multiples of pi over 6, pi over 4, pi over 2. I would memorize those. That will speed up your worksheets and the test. So, multiples of pi over 5, so this is pi over 6. Let's do a version of pi over 4. It's actually even easier. Pi over 4, do you remember that the top half of the circle is pi? How many pieces am I cutting it into? Pete?
You're cutting it into 6 pieces?
For 30 degrees, yeah.
Oh, 45,
The top half of the circle.
4 pieces?
4 pieces. 1, 2, 3, 4. See why? Where is this? Anybody? In degrees? Good. 45 degrees. Does everybody see this is pi over 4? Because the whole thing is pi? I'm going to mark these. Can somebody give me the sine of 7 pi over 4? I do not. How do you do that? Like, it's a multiple of pi over 4. How many of them do we need? Yeah. Here's 1 pi over 4. Where's this? Give me the sign there. Radical 3 over 2 would be a multiple of 30. So you're doing 45, 45, 90. It is a radical, isn't it? Radical 2 over 2. Positive or negative? Negative radical 2 over 2. And by the way, that is the only option for sines and cosines around the circle. Let's try another one. Cosine of 119 pi over 4. How on earth do you do that? There are several ways. So big, take this one. By the way, everybody look up here for a second. You could count this out. 1 pi over 4, 2, 3, 4, 5, 6, 7, 8. And you can just keep counting until you get to 119. But there might be a faster way. Okay, what do you think? Correct. So it's a multiple of, how many pi over 4s do we need? 119 of them. How many of them do you get going once around the circle? 4. Arhan? How many pi over 4s do you get going once all the way around the circle? That's the top half. 1, 2, 3, 4. 8. See one? All the way around the circle is 2 pi. So you get 8 of these pieces. I want to get 119 of them. Can somebody speed this up for me? Where's that again? Yeah. You can divide it by 8. And you find out, in other words, what's the biggest multiple of 8 you can get in here? Well, think of a nice big one. We go 119 times 119 of these notches. Does it make sense that if I go once around the circle, it's 8? How about if I go 10 times around the circle? How many notches? 80. That'll get us back to where we started. So there'll be 39 left. Keep going. Every time you go 8, this should remind you a little bit of like the multiples of 4 when we're doing imaginary numbers. This is just multiples of 8. You can keep subtracting 8, I suppose, if you want. What's a big multiple of 8 that I can still subtract? 32. What is left? 7, yeah. Does that make sense? So if I go 10 times around the circle, that covers 80 of them. And I go, what's 32? 4 times more around the circle. Now I have 7 left over. 1, 2, 3, 4, 5, 6, 7. Where are we? Go ahead. In other words, where was this? Here was the sine, cosine of 119 pi over 4. What's the cosine here? Yeah. Positive radical 2 over 2. Once you figure out where you are in the unit circle, done. Yeah.
So what are the other, radian values for like 45, 135,
Ah,
225?
okay. This is 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4. And some of them reduce, some of them do not. The odd ones do not, that's actually kind of handy. This would be 1 pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. You just skip them. 1, 2, 3, 4, blah, blah, blah. Okay. Try one more. Again, it's hard to start thinking in radians if you've been thinking in degrees all your life. But if you just sort of switch off that part of your brain and pretend you're an alien, and say, I'm just thinking in terms of chunks of weird stuff. Like we think in terms of base 10, naturally. But that's kind of because we're trained in it. We didn't come from the cradle thinking base 10. We were taught base 10 by our parents and by our teachers. Our parents could easily have taught us base 7, and that would be as natural to us as base 10 is now. And it would be weird, normally people wouldn't do that unless we had 7 fingers, like, like a hand and a lobster claw or something. But it still makes sense to anybody who's been taught that way. So if I teach you in chunks of pi, you can think in terms of chunks of pi. Can anybody tell me what 90 degrees is in radians? Give this a shot. Pi over 2, good. Look up here. Here's 0, right? 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2. That's what thinking in terms of radian chunks looks like. You can always reduce them. By the way, you remember my rule when you were doing this stuff? If you write this on a test, I will only take off like 1 point out of 10. It's much better than putting the totally wrong answer where you lose 7 or 8 out of 10. See? Because this is correct. Reducing is a much, much lower point loss than having a wrong answer. So I would recommend, like over here, if you did this, if you just said 2 pi over 6, 3 pi over 6, and just left them like that, I would not take off much. So if there's a choice between getting the wrong answer and just playing it safe, play it safe. If you lose 1 point out of 10 for every single problem, you've got an A- on the test. Make sense? But if you get the wrong answers, like if you get like pi over 6, pi over 5, pi over 4, pi over 3, pi over 2, pi over 1, and I said, oh my goodness, what are you doing? Then that's when scores get really scary. Okay. Don't be afraid of counting in terms of these new chunks, even if you forget to reduce. It's much, much better if you don't. So try this. What is the cosine of 237 pi over 2? First of all, you see what the base angle is. Here, the base angle is pi over 6. It's 30 degrees. Here, the base angle is pi over 4. It's 45 degrees. Here, what's the base angle? In other words, when I ask about 5 pi over 6, the base angle that's buried in there is pi over 6.
Yeah, pi over 2,
It's pi over 2.
which is 90.
That's 90 degrees. This is a certain number of 90s. Does it make sense? How many of these 90-degree chunks do I get all the way around the circle? Okay, what's that? 4. What if I went twice around the circle? 8. What about 10 times? 40. What about 100 times? 400. I want to hit 237. Can anybody think of a relatively speedier way to count? Go.
236.
Let's try it. 236. If it's a multiple of 4, you're in business. Let's try it. Is 4 going to 2? How many times is 4 going to 23?
Isn't that 25 times?
5 times. So that's 20 with a 3 left over. 4 going to 36? Yeah, how many? 9. That basically says you've gone 59 times around the circle. How much is left over for 237? Yeah, this is 59 and one fourth. So what I did was 59 times, back at the beginning. Give me one more. What's the cosine? Wait a minute. 0. Theta. All right. Let me grab the worksheet for you. Should be in the photocopier. The worksheet, the first 6 problems are just once around the circle, but everything is in radians. So hang tight for just a second. I need to explain a few things before you break it. So hold tight. You want to take a minute? Rolling. So take a look in here. Front page. 1, 2, 3, 4, 5, and 6. Just give me once around the circle. All the solutions between 0 and 2 pi. The second page, 7, 8, 9, 10, 11, 12. I want all of them. How do you get the multiples in radians? Let me give you a solution that we had before. This is probably the last thing I have you put in your notes. Cosine of theta equals radical 3 over 2. Can somebody tell me the solutions? E degrees. Just one on the circle.
Pi over 6.
In degrees.
Oh, 30.
0 and 360. Go ahead, what is it?
30 degrees.
Yeah, if you use the unit circle, it's over a lot. So 30 degrees, and where are you?
And 330 degrees.
330. Now, that equals 30. That equals 330. What if I had you do it with all real numbers? How would you change the solution to row? Go ahead.
The pi over 6 and 11.
Not radians, but just all the solutions, all the repeats. Like what we just did in the worksheet.
Equals 30 plus 360. K.
Degrees K, where K
Is
is an integer in years, and then same thing here.
thing.
Now, you anticipated what I'm about to ask. What if I wanted in radians? Can we think of 30 degrees in radians? B?
Would it be over 6?
Yes. So I'm going to switch this over. Theta equals pi over 6, which is great. And let me know what 330 is. There's several ways to get it. You can do the conversion, 330, but there's an easier way. Exactly, 11 pi over 6. Because if this is 11 times bigger than this has to be 11 times bigger than this. How do you get all the repeats? I'll give you a hint, it's almost identical, except you need to convert this to radians. And it's quite easy. It's plus, go. Plus 2 pi k, where k is an integer. Plus 2 pi k, where k is an integer. That's what you're going to be doing on this worksheet. Numbers 7 through 18. Now, the assignment for tomorrow is not the whole thing. The assignment is 1 through 9. So that means there will be half of the forever ones in radians you don't get to. And then 13 through 18 is in radians. Oh, by the way, On the top of the page of the last page, do me a favor, write in the word radians. On the worksheet that is at 13 through 18, it says solve each equation for all values of theta. Please put the word radians. That means I want the solutions to look like this. It'll be something radian plus 2 pi k phase negative. That'll be true for 7 through 18.
And for seven, you want the equation?
For 7, they gave you the equation solve for theta. You know, what thetas make that work?
Oh, yeah.
Wait, so all these are doing radians or just 7 do?
All of them are in radians, but the front page is just once around the circle. The other ones are going to have the repeats.
Oh.
Yeah, so everything's in radians on this. Let me scan through this, by the way. The 7F, right? Let me give you a warning, see if any of these are no solutions. No, every single one of them has solutions. Congratulations. All right, it is all yours. Go ahead and pound away at this. And call me over to this. And I'll email these to Gianna. God bless you. Recover your health soon. See ya.